Gravity Rediscovered, an attempt to make uncommon sense common. At the very start, let's ask some funny questions. Does matter hide gravity? Is space-time rotating? Or more specifically, is the gravitational field rotating? Can space-time be extracted out of mass? Is time a scale or an element of the reality? Is time a relation between gravity and space? Let's even invite answers that create questions. Only in order to arouse uncommon thoughts, we link parameters that are not usually linked. That's because thinking is linking and thinking is seeing the unseen. Let's try to see the unseen. Let's try to feel our thoughts and think our feelings. It's important to be aware of some facts that are usually conflicting with our intuition. For example, when two bodies attract each other, each of them experiences the same force although they differ in mass. Let's make sense of it. Here are two celestial bodies, one bigger, one smaller. According to Newtonian law of gravity, the force of attraction between the two bodies is given by Fg equals g times m1 times m2 over d squared, where m1 and m2 refer to the mass of the two bodies, and g refers to the gravitational constant, and d refers to the distance between the centers of the two bodies. Obviously, the same formula is used to measure the force experienced by each of them, whether big or small. That's why the force of this attraction is called the force between the bodies, not the total force. There is no total force here. The body with the smaller mass attracts the body with the greater mass, but its force of attraction gets converted into motion, or the velocity it has. Whereas the force of attraction exerted by the greater body converts space-time into the gravitational field in which the smaller mass gets its velocity. Another very important thing in this regard is that the forces act in opposite ways, not toward a common point. This is very important. That's why this is the right direction of the force. And this is the wrong direction. Let's look at the right direction again to have a better feel. This means that each one attracts the other toward itself. It's like a tug of war. You get pulled by pulling toward yourself. The pull is the gravitational force. The rate of change in the force over the field is gravitational acceleration or gravity. So, gravity is a property of the field, which Einstein calls curvature. The theory of general relativity doesn't even call gravity a force, as it focuses on this property. Earlier, the question haunted inquisitive minds: how can the action be possible at a distance? Now, after defining the field, we can say that the action is possible because the distance itself is active. Another very important fact conflicting with intuition is that even increased mass will not cause one to fall into the other. And it's not very difficult to understand this. When the mass of the smaller body is increased, it experiences a greater force, and at the same time, its centrifugal force also increases. Thus, the increase in mass balances the two opposite forces. This is a hypothetical situation. We are only talking about a situation that we see if the mass increased, and this is not the reality. And here is probably the most important fact about gravity. Just think, the most important. The fact is that the velocity of the smaller body does not depend on its own mass. It's very interesting. In fact, here lie the most important secrets to the universe or to space-time. Let's think about it visually. The less the distance between the body and the central mass, the greater is its velocity. In other words, if you go farther and farther away from the central mass, you will have a smaller and smaller velocity. Here's another fact to be noted with special care. If you vary the amount of mass on the same orbit, the velocity will not change according to the mass. That's because in a specific orbit, the velocity is always the same. But why is that? That's because the velocity only depends on the central mass, not on the mass of the body orbiting. That means each orbit is a velocity line whose velocity is already fixed. And here's another issue which is equally important. Gravity changes with mass and distance. But that doesn't mean that gravity is dependent on the body orbiting. On the contrary, gravity is only set as a property of the field by the central mass. And this means that a specific value of g can be set for each orbit. So we see that neither velocity nor gravity is dependent on the body orbiting. Rather, both of them are dependent on the central mass. So we see that both gravity and velocity increase downward. That means toward the central mass and decrease outward, away from the central mass. And neither of them is dependent on the body orbiting. We mean on the mass of the body orbiting. For the sake of clarity, let's repeat the central issue here. Just as the velocity of an orbiting body does not depend on its own mass, the acceleration of its falling speed also does not depend on its own mass. This is also very interesting. And this idea first came from experiments. Consequently, whatever the mass of a falling body is, its acceleration downward will always be the same. That's because the acceleration doesn't depend on its own mass. Here we see that the calculation of the free fall time, the time an object takes to fall to the ground freely, doesn't involve the mass of the body falling. So, what it means is that free fall is a consequence of the property of the G field only. And this is what inspired Einstein to invent the idea of the curvature of spacetime. Now let's focus on the relation between gravity and velocity. Gravitational attraction between two bodies, G times MO times M1 over D squared, and the centrifugal force experienced by the smaller mass, M1 times V squared over D. By definition, these two forces are equal. So we have this equation. Solving for V, we have root over of G times MO over D. This is the formula for calculating the velocity of a moving body. In this case, it's to be noted that m1 is cancelled out from both the sides. This means that the velocity is not dependent on the body moving. Rather, it only depends on the central mass. This is another way of saying that velocity is a consequence of the property of the d field, which Einstein calls curvature. Now it's easy to see that the velocities associated with the different levels of orbits are calculated by using the same formula. And because the only variable element is d of the distance, the velocities change only because of the change in the d, which is just to be identified as a property of the g field. Here again we show that the shorter the distance from the central mass, the greater the velocity. It's as if the velocity lines were set in advance, predetermined by the central mass. Here's an example. Information about the central mass and the distance between the central mass and the orbiting body is given here. We have to calculate the value of g due to the central mass at the center of the orbiting body and also the velocity of the orbiting body. Actually, we have used the information about the sun and the earth, and we have got the results correctly. Here again, we see in terms of a real example that neither g nor v is dependent on the orbiting body's mass. And both of them are consequences of the property of the g field. We are saying the same thing again and again and again, only to reinforce the learning. The gravitational field can be imagined as a structure of the pathways governing the movement of other bodies in it. Here's another example: mass of the Sun, MO, distance between the Sun and Mars, d, velocity of Mars, to be found out, g of the Sun at the center of mass, to be determined. What's the relation between this g and this v? Let's work it out. The same calculation done in another way. Here's another example. We've used real information. Let's also do this. A planet is seen to be orbiting a star at the velocity of 29.8 kilometers per second. Its distance from the center of mass of the star is 149.6 times 10 to the 6 kilometers. What's the mass of the star? So, we learn that if we know the velocity of an orbiting body and its distance from the central mass, we can determine the central mass. Now, a very important issue: gravity and density. We have talked about mass, a point away from the celestial body, the gravitational acceleration experienced at that point, the force of attraction between two bodies, and the velocity of an orbiting body due to gravity. And we know that we usually work on R, T, M, V, G, and T. And we know that we need the value of the distance in order to find out the value of G. But in fact, we can find out the value of G without D. Let's approach the topic in an unusual way. For the time being, let's say that matter hides space-time. Einstein said that matter distorts spacetime. So we haven't said anything different. Let's suppose that this is the Earth, and let's imagine it denser and denser and denser. Just imagine that somehow it's getting squeezed. The mass m is unchanged, but the radius r has decreased. Because the volume has decreased. This means that d in the following equation has decreased. And a decreasing d with the other things unchanged means an increasing g. It's an issue of great interest. On the face value, it seems to be a mental exercise. But it does represent the reality also. Suppose this is the original volume of the planet. So in its original size, we could talk about a point like this, which is lying on the surface of the planet. But we couldn't talk about a point like this, which is inside the matter. Or in other words, occupied by matter. But now the point is released because the matter has been squeezed into a smaller volume. As a result, the value of d has become very small, and consequently, the value of g has increased greatly. It might look like a mathematical manipulation, but this mathematical possibility represents the reality too. And consequently, it has great and important implications. The density of mass is calculated by dividing mass by volume. In this way, we can find the relation between r and d, that is, radius and density. Obviously, as d increases, r decreases. In other words, as r decreases, d increases. The same thing can be said in this way too. As the volume decreases, the density increases and the r decreases. Consequently, gravity increases by squared multiples. Let's do an example to solidify our understanding. The mass and density of mass of a planet are given here. We have to find the radius of the planet. Now, by using the formula we have constructed, we can ask questions like, what would be the radius of Mercury, Mars, Jupiter, or any other planet or moon if its density were the Earth's density? The information collected in this way might be useful in comparative purposes. Or we could also ask questions like, what would be the radius of Mercury, Mars, Jupiter, or any other planet or moon if its density were 1? Or even a question like this: what's the value of G on the surface of a planet whose density is 5,515, for example? We calculate the value to be 9.81, which shows that we have used the information about the Earth. What it all implies is that by observing the velocity of the orbiting body, you can tell what density the central mass is. If you know the distance, now let's look at the distance-velocity relation. If we set the velocity to be c, that is, the speed of light, then we have this formula: d equals g times m over c squared. But the fact is, nothing can move faster than light, not even at the speed of light. So, this can happen only inside a black hole. That means we have to find the outside of the black hole farther away. So let's look for an orbit at twice the distance farther away. This, in fact, is the Schwarzschild radius. If the planet's size shrinks beyond this, it has to get transformed into a black hole. We have used twice d in the place of d only to match our calculation with Schwarzschild's findings, and this is not our discovery. Schwarzschild found this equation by solving Einstein's field equations. We just tried to understand it in our own way. Let's leave a question here for the next video. Is the gravitational field rotating? If you say yes, then another question crops up. Is it rotating in the three-dimensional space? And the answer is no. That's because if it were, then the velocity would be greater at the outer edge of the field. And if you say no, it's not rotating, then still another question crops up. Then why is the velocity set by the field itself? Why are objects placed in the field have specific velocities at specific points? In other words, why is the velocity a property of the field itself? Well, let's be bold enough to ask another question. Is the gravitational field rotating in time? Then again, what does it mean for something to be rotating in time? And how do you explain the related phenomena if it's not rotating at all? We plan to discuss all these points in the next video. And many more new things. Now let's do some more exercise.